I truly enjoy what I do. Not only do I have the possibility to code for a living, I have the possibility to write software which can save lives. Behind me you will see a breathing ventilator, which we developed by ourselves. So we are specialized in creating sophisticated user interfaces on reliable, safety-critical devices. Today I'm sharing our expertise and our experiences while we were building a mobile ventilator tester, which is basically the device you see on the right, which you will use to verify that ventilator. You can imagine it like an oscilloscope for a technical service engineer in a hospital, which verifies that your breathing ventilator works as expected. So this device, you will see in the background how it's organized. So me and my team, Roman the hardware engineer, Mark the mechanics engineer, Philip and Marco on the software, we created this astonishing device. So what it does, it basically measures the airflow, the pressure, the temperature, and has some algorithms to calculate all the various breathing parameters. So interesting for this conference is the top part, which is our customized Android platform. So we basically reuse Android for simple user interface. So let us go through the challenges we faced while we were creating this beautiful piece of engineering. So the simplified system architecture is that we have a bare metal controller on the right, which does all the signal processing and sampling in real time, which means we have exactly 5 milliseconds, so it's 5.0001, so it's real time. So it collects all the sensors, and when it made a batch of all those sensors, it transfers it to the UI board. So the UI board is our custom hardware. We have our custom BSP running, and we have our own application running on it. But as a developer, when you're in Java world and you make a software which looks like this, your product management will not be happy. So remember back, the problem we faced was that the data we collected on the hard real-time system is sent out at 200 Hertz to the UI. So we have 200 times per second, about 10 sensor values and about 20 to 30 parameters sent constantly to the UI. So you all see, I think most of you know where the problem is coming from, and Android has a nice tool set. So if you see that kind of aggressive garbage collection, you know immediately that it won't work in your application to have a smooth user interface. But thanks to the documentation and the really nice platform and the tools it offers, I will show you how you can do it by yourself to analyze such problems and find solutions. So let us go through the steps what's required in order to have a little less aggressive garbage collection. Still, Java is still heap oriented, so it's not worth it, I guess, to eliminate it fully. But with a garbage collection event around each 10 seconds, you get a smooth frame rate for your visualization, and the user has a smooth UI experience. So where do I come from? My name is Michael. I'm a software engineer and a project leader, but my real heart belongs to microcontrollers and hardware stuff. So what do I have to tell you about Java? Well, as he told, 1 year ago we started that project. So coming from another background and not from the Java world and coming from below, from assembly and C++, I share my pitfalls and the problems I faced with Android. So our company is specialized in developing medical systems, embedded systems, and industrial automation. So the 4 steps, or the 4 parts which you require to build your own custom device are mainly the hardware. You need your own Android OS, so which matches to your hardware. You need your app, and you need some kind of update infrastructure. So for your hardware, you have to find a CPU, you have to find the memory, the flash, display touch, the connectivity solutions, and the power supply. So most of you app developers ask, why you do it yourself? You can just buy a phone. Well, in an industrial field, it's a little bit hard. So the amount of chips you can get, which are available for 10 years, which have customized temperature range, and which you as a customer can buy, are limited. So all of you agree that if you build something like that, it's not very professional. So I really recommend to have a look at that. That's the worst tablet computer I've ever found. Just have a look how it's built. But we at IMT, we believe that you should do it with passion and with love. So basically this is our custom board where the Android is running on. So it's kind of old school Android lollipop, but for us that's enough. So we just need the material design and the new art runtime, which has a lot of improvements. So it's kind of low-end device with 1 GB RAM and 4 GB of storage. But for us, the temperature and the power consumption is more important than having real fast processors, because this will increase the price. And your hardware engineer will yell at you because it just creates too much heat and it consumes too much power. So if you compare the processor, how that you know in which field I'm operating, just the yellow part is our board, and if you compare it to the cheapest phone I found, which is the Vicoleni, you can buy it for $50. It outperforms our current chip by factor 2 in the CPU, and the RAM throughput is better, I think also double, and the UI experience from Atutu is also mentioned as double. So you think, double, that's not a problem. But if you compare it to the latest devices like the Nexus 6P, which is the blue one, or the astonishing NVIDIA TX1, it just outperforms our chip by miles. So writing a software on a real fast platform is kind of easy. So the previous example runs perfectly smooth on all our smartphones. But on our custom device, which is kind of low end, you will face various challenges. So how do you build your custom operating system for your own hardware? Well, it's very well documented from Android. Basically what you need to address your chip, which is inside the device. Basically you need to set up all the clocks, all the RAM timings. And I guess some of you which are familiar with hardware design, you have to tell which pin is where it belongs to. So that's basically this embedded Linux stuff you have to do. You have to adapt the kernel to your own hardware platform. And then you have to consider the power consumption, and you have to consider the heating. And then at the end, the worst thing which every developer forgets, you need to make it producible. So a company has to build those devices. It's a manufacturing process. And then you have to flash your BSP to it. So it's not... Nothing is running on the chip, so somehow you have to teach him to load that code. So there's no update server, you have to do it with JTAG wires or whatever. So with the BST, I think Joanna mentioned it before, there are those compatibility test suite which we will run after the BSP is implemented, so that you can be sure that the part you implemented is more or less working as expected, so you don't have any crashes because you made some wrong RAM timings. Just you can imagine you have to run your temperature test in a chamber that it operates at 5 degrees, you have to run it at 50 degrees. So that's really hardware low-level stuff, which I personally love. Now the next part which you're more interested as app developers is the app. So basically, how did we do that? So from user point of view, it's nothing really interesting. There's a chart. It shows the value. So basically, you can zoom in. And if you're more interested to see even more data, again, you can use your gesture to zoom in even further. So I think now you soon see the point. It's constantly updating, so it's sending the data with 200 Hertz really fast. And now the user wants to see all the 30 seconds. So from the user point of view, it's as he would expect. So it's like a typical app. It's nothing really special. The key point here I'm talking is how to handle this massive amount of data without really killing your UI performance. So a really nice article I like was, it's published on Medium from Google, is developing Java for Android, which for me, coming from C++, is really helpful because, of course, I learned Java and I know C#, but there are a lot of pitfalls you can run into when you do performance-aware programming with Java. So Java, as all of you know, is really heap-oriented language. And on our system, the real bottleneck is the memory, as on most devices. So Java is not like Swift or C++, where you can put a temporary object on the stack, which is on the real, usually on the real fast RAM. So you always have to go to the heap, which is, so you create your object, you have to run to the heap. Okay, you get it. Then you modify it, and then you throw it away. So the big fat garbage collector later has to stop you, has to collect all the garbage you created, and then you can continue. So imagine doing that 200 times or 2,000 times a second with massive amount of data will not work. So what do I mean about architecture? So if you mix activities, fragments, layouts with a lot of libraries, I believe the outcome is not an architecture. So it's nice software maybe, it works, you can read it, but somehow a concept is missing. So if you run it through the mixer, your code might look like somewhere spaghetti code. It's not, you don't see a clear point, or it's either really hard to dig into. So the bigger the software gets, the harder it is to see how it's structured. So coming back, when I talk about architecture, what are the key functionalities of that device? Basically, you have to read the binary data from the measurement controller. Basically, he doesn't care. He just throws the data at you with 200 hertz. So you have to read it quickly, else you lose. And then you have to convert that data into a more sophisticated structure. I will talk about that later. And in the end, you have to update your chart and your numeric values. That's basically the task of the UI. So we all know that you should offload as much as possible from the UI thread. So let's take those concepts or the key functionalities the app has to do. So let's say we create a communication thread, which is responsible to grab the data from the serial port, decode the data. Then we have a processing thread, which converts this binary data into a big sample. So sample means all data which belongs to the same point in time. So at 0.005 seconds, I collected this amount of data. At 0.10 seconds, I collected this amount of data. So you have big piles of measurement samples. Then, of course, you have the UI thread, which has to update the data to the user and to the chart. And then you have the OpenGL render thread, which should, in Dream World, he should render the data for the OpenGL parallel to the UI thread, and whenever it's ready, it will transfer the data to the UI thread. So on a 4-core system, for example, you would have 4 independent workers, which you could balance really well, and so you loaded as much as possible off from the UI thread. So I hope most of you remember the talk yesterday from Hannes. So he had a nice example with biological cells. Why do I talk about biological cells? Our way of expressing software is like functional units. So basically you have a part of software. It's a component. You can name it whatever. We name it active parts. You can name them actors, active objects, Java, RX Java threads. So you have an input, and what it does, it computes something, it remembers something, and it generates an output. If it doesn't generate an output, well, what's the point of it? Maybe it triggers some hardware, but you get my point. You tell him, here's the data, convert it, and it will create the measurement sample. So back in our example, let's say we have the communication thread which receives the binary stream. So his work is basically to find the frame. Doesn't matter which protocol you use. Basically, he's decoding that stuff from the serial port. And what he creates primitive data structures. So, of course, all of you agree that we cannot transfer JSON objects through a serial port because it's text-oriented. We have to compress it binary in order to transfer it as fast as possible. So then the processing kicks in, and his job is to do, his input is the primitive data, and he has to convert that into more sophisticated objects like volumetric flow, pressure, temperature. And then there's the UI thread which runs a little bit slower. So his job is to draw the chart and to draw the numbers and maybe as well kick the OpenShell thread. So remember, the communication thread receives data at 200 Hertz. Processing is processing the data at 200 Hertz. And the UI thread is running in 60 Hertz. And let's say the chart is running at 30 Hertz. So of course, we didn't reinvent the wheel. So asynchronous programming with this concurrency is already solved in Android itself. It's called the actor model, or if you have a look, the looper threads of Android, they're basically what we found kind of perfect match for us. So how it works, it has a thread where it receives messages in an ordered queue, and it can generate new messages to send to other threads. So inside the UI thread, you don't have to think about concurrency, because there it's a safe world. So just have a look in the source code of Android, for example. The important part is the handle message. So that's the main activity source code. And what it does basically, it decodes which message it receives with the switch on line 1370. And as a Java developer, you would think why it doesn't use reflection or whatever. So the reason here is to quickly decode and make the cast instead of going through a lot of calls. Basically, when you do a switch case and then you cast, I think, let's have an example. On line 1329, you can quickly cast the object, and then it's much faster. So our notation, coming back, imagine that is basically a handler thread. So it has an input, it receives data, and it has an output where it can create new messages. So with our notation fixed, so you can imagine those are 4 looper threads, which basically the communication thread you remember from previous example, generates raw data. The processing thread, the FIFA queue receives the data, so it sends data to the UI, and it sends data to the trending. Trending means when you're working with that device, you would like to log the data into a database, to a file, whatever, so that later you can analyze that data. Of course, the software still has even more objects, but let's focus on the hot path, I would like to say, where the data is constantly running through at 200 Hertz. So let's have a code example how that looks like to connect those handler threads. So remember our chart. So you see the communication component, you see the processing, and you see the UI. And then we have so-called channels. So the channels are responsible to decouple the sender from the receiver. So communication looper thread has no idea where his data is going to. And the processing looper thread has no idea where his data is coming from. So the data is coming from is already solved by the looper thread because it has a RX queue. But remember that in typical looper thread code, you would always have to glue them together. Somehow the communication thread knows the mailbox of the processing knows the mailbox of UI. But for testability, that's not so nice, so you cannot isolate those components. So that's what our channel is for. Basically, you just connect those mailboxes together, so it decouples. But it's nothing really sophisticated, it just knows the handle of your in-queue of the looper thread. So the code example for the raw data, basically you have primitive data types, which the communication part created. It consists of primitive types float, double, boolean, flags, whatever. There are a lot of more, but let's focus on 4 values. And remember, the output of the processing engine was measurement samples. And here you see we don't use primitive floats. So in proper science projects, you shouldn't just rely on float and doubles. because I think you all get the idea when you work in international teams and your flow is, or your pressure is in millibar, and the other one is used to work with PSI, you can easily get a mess. So if you use primitive data types, it might be a problem of bugs. So coming back to the code example of our processing, what it does, execute is the entry point. It's like the looper thread when it receives a message. And what it does, let's focus on the important part, it creates a new entity of a measurement sample. It creates the volumetric flow, the volumetric, or the pressure. It builds it and it sends it. So on here, we just send the data and we say, I don't know who receives it, but we send the data. But I think you all get the point. If you look at the number of news involved in that function, and if that function is running 200 or 2000 hertz, then we will thrash the memory. So to get the idea how long such a structure is, just what a sample looks like. So that's the structure of the data which is collected at 200 hertz. So we have a lot of fields, and you can imagine that's a lot of memory. So doing an excursion before we go to the memory optimization, I would like to explain you why we rely on units and quantities. So quantity itself is, for example, take a pressure, take a temperature, and the quantity can have various units. For example, a pressure can have Pascal, torr, PSI, and for example, the temperature is in degree Fahrenheit, degree Celsius. So that's basically our pressure class, which extends quantity. I will go through the code quickly. It's just an idea that you get. You can have the pressure units with various types, bar, millibar, PSI. And as an example, what I like, which is nice type-safe code, I can create the pressure. For example, now the ambient pressure is maybe a little bit less than 1030 millibar. But if you would like to get the pressure in inch H2O, you can just get the value, and then you don't have to do the conversion every time. So it's type safe. You can pass that pressure object to anyone, and he can type safe, get the value he likes. So having the same example with primitive data types, you can see easily that in a big project you will get a real big mess if you do it with primitive types. So everyone does the conversion himself. And all of you, I guess, know the examples where a lot of projects failed because one team was working in inch, the other team was working with meters. So the compiler doesn't help you. It's up to the runtime, and we believe working with complex types is better. But working with complex types gives you another problem in Java. It creates a lot of memory, and you will thrash the heap. So we had a look at the JSR implementation, the Units of Measurements API, which is a proposal for Java. But because it's coming from the Java world, it uses a lot of sophisticated Java features which don't scale well on Android. So our focus was to have type safety at compile time, and the most probable unit is already pre-calculated. So if someone fills the data and the other one takes it out, there's no need for computation. So to explain, maybe the JSR is really nice approach from engineering point of view. It does everything in SI units, but you have to do the conversion every time you get the value or you set the value. Yeah. So then now imagine those big objects. I really like that guy. He has a lot of videos and really well documented examples. So coming back to our example, we see that the communication sends data 200 hertz, the processing sends data to the UI 200 hertz. I think all of us agree if we just push 200 messages or 2000 messages per second inside the UI thread, he won't really like it. So, of course, software engineering is always exceptions. There's one exception we have to do. We have to decouple the UI thread from all the other parts. For example, if the UI is a little bit laggy, or if you wrote a little bit bad code, which takes 10 milliseconds to run, the worst recover strategy you can do that you ignore it. Imagine here is data flowing. The UI thread wasn't able to process. So the UI thread is here. His queue is filled and filled and filled even more. So if you simply ignore it and you still flush data, the worst thing what happens when the UI recovered, what will happen? So the UI thread has to work that amount of data, which is a real big stack. But the user is not really interested in really old data. What he likes to see is the latest data. So that's why we need an exception, which is our so-called recycle buffer. So recycle buffer is basically it's a heapless ring buffer which overwrites itself, and it's really kind of lockless. So I will go through quickly what the recycle buffer is. The goal was to program it as heapless as possible. So now it's real heapless. And for a single producer, single consumer, you can program it lockless. Basically, the idea is from the two-lock queue from Michael L. Scott, which in Java is the concurrent queue implemented. But having a look at the concurrent queue, there's one problem. If you add a new element in, or if you take an element out, you will thrash Mr. Heap. So every time you create a new node, a small object is created, and every time you take out an element, you will generate some garbage. So doing that 2,000 times a second still hurts you. So basically, how such a queue is built up, you have a tail and you have a head. So a producer can add new elements to the tail, and the consumer can take the oldest elements out of the head, which in a single producer, single consumer, you can use that lockless. So there's no need to synchronize anything. So it's real parallel programming. And let's take the example. The producer is enqueuing new data, while the consumer is maybe doing it a little bit slower in batches. So in that world, you don't need any lock. But of course, you cannot compute the size. You can just grab elements. And what our approach was to have a second queue, which is called the empty queue. Whenever the consumer has finished that data, he will put it back to the empty queue. So now we have kind of a heapless approach that when you have an object, you enqueue it. It goes through the data queue. Whenever the UI is ready, he takes it out. He fills the data and he puts it back to the object pool. So with those two queues, you have a heapless approach. And so the UI can run at less frequency than the producer, and there's no need for synchronization. So it's a lockless approach. But what happens in overflow? Now you will change to a multi-producer, multi-consumer environment. Imagine that your producer is running really fast. You will consume all empty elements, and you say, I just want to buffer 5 seconds. So in a traditional C++ ring buffer, you overwrite oldest elements. But in here, it's kind of special, because in Java, we would like not to trash the heap. So what it does, it takes out the oldest element before the UI thread was even running, so it overwrites itself. So it's basically then a multi-producer, multi-consumer queue, and the UI thread can run at 30 Hertz, 5 Hertz, whatever. The worst case, what would happen, he will lose all the data. So having a look at the API, it's basically you get your element, and then you can do whatever you like with the object. You can hold it for 5 seconds. It doesn't matter. There's no lock. And when you're ready, you commit it. And then the consumer can read the next value, which is in the buffer. And whenever he's finished, he will recycle it. So that's the approach of our recycle buffer. And just now, having a look at the code, you receive the data. And instead of creating a new object, you get your object from the pool. You fill it. You update the data, and you commit it to the buffer. So that's now the heapless approach to transfer data. So, to get to the summary, basically with that memory optimization, we were able to get a less aggressive garbage collection, which results in much smoother UI. And the task was basically done. So, when you build your own device, you cannot rely on the Google Store. Because what happens when they change a requirement, or that you need to, for example, they say now you would like to be independent of them. So it's nothing really tricky. You just need your own server where you publish your APK or your image of the operating system. So the device has Wi-Fi. It just grabs the APK from there, and it updates itself automatically. So that's nothing sophisticated. Just keep in mind that maybe running your own server infrastructure will cost you some money, but to be independent, it's worth it. Yeah, so I think I truly enjoyed to work on that project, and I love Android platform. It's really, really modern, and I love the tools it offers compared to other industrial platforms. But my summary, I guess, there are not so many people who are actively doing the mechanics, doing the hardware, doing the BSP, and doing the application. It's rough, but I think it's definitely worth it compared to other platforms. Yeah.
Thank you, Michael. That was serious stuff, and if you want to know even more, you have to ask questions.
Hi. What is the reason you choose to use Android and not some real-time operating system instead of it?
Yeah. Basically, the product itself, the real-time part already existed, which is bare metal. And for us, we just reused Android as a UI platform because we really like the toolset it offers. For example, if you compare to Qt, Windows, whatever, the idea was to have a technical project to see what it's capable of and to build up knowledge internally. So because the real-time part was already implemented, and there's no need to run it on the same core, so we have a 2-processor system. For example, UI can crash. So I cannot really say that I understood all 40 million lines of code of the Android BSP. So I thought the safety critical part should be done on our specific system. But I agree it could be done on a single chip where you do the sampling in real time. But for us it was the tool and just reuse Android as UI framework.
Hello, thanks for the talk. So with such big amount of data, is there any persistent solution? How do you save this data to the device? Or
Yeah, basically it buffers the data inside RAM. For example, you saw the trending component, which then is kind of a batch processing with low priority. So if we rely on the scheduling of Android, which then just flushes the data into a database. So that's the approach we will go.
But with such continuous time data that's flowing all the time, do you have like overflow in your database, or your database can handle all this stuff? So what kind of database that can handle all this data and keep them consistent and reliable?
Yeah, basically we just use some kind of a ring buffer example where if you have the data pre-allocated and you just overwrite the oldest, it has a timestamp, and then you cannot trend for like 4 days because you're running out of storage. Basically, it's kind of a ring buffer for that implementation.
Okay, thanks.
Thank you. Yep.
Hello. I would like to know regarding the UI you used. It looks like you design a custom component, a custom view. Did you encounter any problem there in synchronizing, drawing? I mean, this also has issues, I guess.
It's a nice example. So consider when you draw your own chart. I think some of you already tried. So consider oversampling, for example, if you have more data than pixels available. Consider undersampling if you have less data than pixels, where you have to do interpolation. So just in summary, yes, we work together with SciChart from England. I guess, Andrew, you're here? No, so he's still working. I think he will publish the SciChart today for Android. So we know them from WPF. So it's a real good company focused specifically on charts. So if you're doing a project with serious amount of data, I would really recommend you that library. So he's a really nice guy, and they have also you can also access the source code. So I think just some things you have to handle autoscaling, you have to handle the interaction. So they do a lot of stuff in C++, and that's why it's fast. And they have their own OpenGL renders. So they also tried with traditional Java approach, but the frame rate was like 2 or 5 hertz. So imagine you have like 3 million data points, and that's where the SciChart is really good at. So I really recommend you SciChart. We developed our own chart library, but for Android, so we teamed up together with them. We sponsored the development, and it will be released, I guess, today.
Yeah, just a second.
With industrial data acquisition, usually it is necessary to have a timestamp. So you had this non-primitive data types, but there was no timestamp.
It was the sampling number. The sampling number is the time when it was, for example, at 5 milliseconds, you say it's sampling number 1. At 10 milliseconds, it's sampling number 2. So that's the timestamp.
Yes, but if this is then processed in the cloud or on a server, the real timestamp, the generation would be very complex. Especially, this looks like a local solution. And to be honest, I don't understand why, if there's a local data acquisition, why must there be a visualization on the same device? So usually the data is...
It's a relative time. You just need relative. You don't need absolute time. So what you need is you work with that device. You see how it operates, and then you read out the values from the ventilator. Mm-hmm. So you make your test, like when you bring your car to the service, they check your Abgase. And then basically they note pass or fail. So that's what the device does. It's just used relatively. And you don't need a specific timestamp in atomic time. You just need relative time. Okay?
Okay. Do I see any more raised hands? Any more questions to Michael? No, I don't see any. Michael, thanks again.